This is SpaceTime, Series 29, Episode 16, for broadcast on the 6th of February 2026. Coming up on SpaceTime, scientists finally determined the thickness of Europa's ice shell, a new case for a possible Planet 9, and sidestepping the Heisenberg uncertainty principle. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have finally received their first clues into the thickness of the frozen ice sheets that cover the Jovian moon Europa. Data from NASA's Juno mission suggests that the ice shell is around 29 kilometres thick, at least it is on the part of the moon where the spacecraft flew over. Encased deep beneath this ice sheet is a global liquid water ocean containing more water than all the Earth's oceans combined. The new findings, reported in the journal Nature Astronomy, were obtained using Juno's microwave radiometer during the probe's 2022 flyby of Europa. The Juno measurements, the first to discriminate between thin and thick ice shell models that have suggested the ice shell is anywhere from less than half a mile to tens of miles thick. Slightly smaller than Earth's moon, Europa is one of the solar system's highest priority science targets for investigating habitability. Evidence suggests that the ingredients of life may well exist in the saltwater ocean that lies beneath its thick icy crust. Uncovering a variety of characteristics of this ice shell, including its thickness, provides crucial pieces to the puzzle of understanding the moon's internal workings, and therefore its potential for the existence of a habitable environment. On September the 29th, 2022, Juno came within 360 kilometres of Europa's frozen surface. During this flyby, the spacecraft collected data about half the moon's surface, peering beneath the ice to measure its temperature at various depths. Juno project scientist Steve Levin from NASA's Jet Propulsion Laboratory in Pasadena, California, says the 29-kilometre estimate relates to the cold, rigid, conductive outer layer of a pure water ice shell. If an inner, slightly warmer convective layer also exists, it's possible the total ice thickness would be even greater. If, as suggested by some models, the ice shell also contains a modest amount of dissolved salt, then the estimate of the shell thickness would be reduced by about 6 kilometres. The thick shell implies a longer route that oxygen and nutrients would have to travel in order to connect Europa's surface to its subsurface ocean. And understanding this process would be highly relevant for future studies of Europa's habitability. The observations also provide new insights into the makeup of the ice just below Europa's surface, revealing the presence of so-called scatterers, irregularities in the near-surface ice such as cracks, pores and voids, which scatter the instrument's microwaves reflecting off the ice, similar to how visible light is scattered by ice cubes. These scatterers are estimated to be no bigger than a few centimetres in diameter, and they appear to extend to depths of hundreds of metres below Europa's surface. The small size and shallow depths of these features, as modelled in the study, suggest they're unlikely to be a significant pathway for oxygen and nutrients to travel from Europa's surface down to its salty ocean. Juno's principal investigator, Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says how thick the ice shell is and the existence of cracks or pores within it are all part of a complex puzzle needed for understanding Europa's potential habitability. He says they'll provide crucial context for NASA's Europa Clipper mission and the European Space Agency's JUICE Jupiter Icy Moons Explorer spacecraft, both of which are now on their way to the Jovian system. Europa Clipper will arrive there in 2030, while JUICE will arrive a year later. As for Juno, well, it will carry out its 81st flyby of Jupiter on February the 25th. Needless to say, we'll keep you informed. This report from NASA TV.
Welcome to Jupiter, the largest planet in our solar system. 300 times more massive than Earth. Juno's main mission is to learn more about how Jupiter formed and how the planet works from the outside in. All we can see now are the tops of the clouds. But Juno's sensitive instruments can look deeper, beneath the clouds and churning storms. Juno's orbit takes it over the poles and just 3,000 miles above Jupiter's clouds, closer than any other spacecraft has come before. These close encounters allow Juno to map Jupiter's gravity, magnetic field, and water. Jupiter is so far from the Sun that sunlight here is 25 times weaker than at Earth. And while there are no astronauts on board, Juno carries 3 Lego minifigures made of aluminum: the Roman god Jupiter, the goddess Juno, and the famous astronomer Galileo, who in 1610 became the first explorer to turn a telescope toward Jupiter. What Galileo saw through a telescope, we will explore up close with Juno.
This is SpaceTime. Still to come, a new case for a possible Planet 9, and physicists have reshaped quantum uncertainty to sidestep the restrictions imposed by the famous Heisenberg uncertainty principle. All that and more still to come on SpaceTime. There's new hope today in the ongoing search for a 9th planet out there in the dark outer reaches of our solar system, somewhere far beyond Neptune. New computer simulations, reported in the journal Nature Astronomy, suggest that planets in very wide orbits around their host stars are not anomalies, but rather a natural byproduct of a chaotic early phase in the development of planetary systems. The authors use complex modelling to show that this phase occurs when stars are still tightly packed in their stellar nurseries and planets are still jostling for space in turbulent, crowded systems. One of the study's authors, Nathan Cabe from the Planetary Science Institute, says the team simulated the capture of planets on distant orbits among a variety of hypothetical planetary systems. And they found that solar system architectures like the Sun's have the highest probability of capturing these types of distant outer planets. He says essentially it's like watching pinballs in a cosmic arcade. When giant planets scatter each other through gravitational perturbations and interactions, some are flung far away from their host star. Now, if the timing and surrounding environments are just right, those planets don't get ejected from their systems, but rather they get trapped in extremely wide orbits. For the study, the authors ran thousands of simulations involving different planetary systems embedded in realistic star cluster environments. They modelled a variety of conditions, from systems like our own solar system with a matrix of gas and ice giants to more exotic systems, including those with 2 stars. What they discovered was a reoccurring pattern. Planets were frequently pushed into wide eccentric orbits by internal instabilities, but then stabilised thanks to the gravitational influence of nearby stars in the cluster. Cabe says that when these gravitational kicks happen at just the right moment, a planet's orbit becomes decoupled from the inner planetary system. And this creates a wide orbit planet, one that's essentially frozen in place after the cluster disappears. The authors define wide orbit planets as those having semi-major axes between 100 and 10,000 astronomical units, distances that place them far beyond the reach of most traditional planet-forming disks. By the way, an astronomical unit, well, that's the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. The findings could help explain the long-standing mystery of Planet 9, a hypothetical world believed to orbit the Sun at a distance of somewhere between 250 and 1,000 astronomical units. Though it's never been directly observed, the odd orbits of several trans-Neptunian objects hint at its existence. The new simulations showed that there's up to a 40% chance that a Planet 9-like object could have been trapped in such an orbit. The study also ties wide-orbit planets to a growing population of rogue planets, worlds which were completely ejected from their host star systems. Cabe says not every scattered planet is lucky enough to get trapped. In fact, most end up being flung into interstellar space. But the rate at which they do get trapped gives a connection between the planets we see on wide orbits and those we find wandering alone in the galaxy. This concept of trapping efficiency, which is the likelihood that a scattered planet remains bound to its star system, is central to the study. The authors found that planetary systems similar to the Sun's solar system are especially efficient, with trapping probabilities of 5 to 10%. Other systems, like those composed of only ice giants or circumbinary planets, had much lower efficiencies. Moreover, this study also identifies promising new targets for exoplanet hunters. It suggests that wide-orbit planets are most likely to be found around high-metallicity stars that already host gas giants, making these systems prime candidates for future deep space imaging campaigns. The authors also noted that if Planet 9 really does exist, it could be discovered fairly soon after the Vera C. Rubin Observatory becomes operational. With its unparalleled ability to survey the sky in depth and detail, the new observatory is expected to significantly advance the search for distant solar system objects, thereby increasing the likelihood of either detecting Planet 9 or alternatively providing the evidence needed to totally rule out its existence. This is SpaceTime. Still to come, sidestepping the Heisenberg uncertainty principle, and later in the science report, a new study warns that people who consume alcohol for longer periods of time are far more likely to develop bowel cancer. All that and more still to come on SpaceTime. Physicists have reshaped quantum uncertainty to sidestep the restrictions imposed by the famous Heisenberg uncertainty principle. The findings, reported in the journal Science Advances, could underpin future ultra-precise sensor technology which is used for navigation, medicine and astronomy. The Heisenberg uncertainty principle, introduced in 1927, says that you can't know certain pairs of properties, such as a particle's position and momentum, with unlimited precision at the same time. In other words, there's always a trade-off in uncertainty. The more closely a property is pinned down, the less certain you are about other factors. For example, you can precisely know either where an object is or how fast it's moving, but not both. But now, researchers have shown how to engineer a different trade-off to precisely measure position and momentum at the same time. Now, according to the authors, the key involves moving the unavoidable quantum uncertainty to places one doesn't care about. In other words, big, coarse jumps in position and momentum. So the fine details one's interested in can be measured more precisely. But of course, even then, aren't you still lacking the accuracy? This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has shown that people who consume alcohol for longer are far more likely to develop bowel cancer. The findings, reported in the journal Cancer, looked at data on 88,092 adults, none of whom had cancer when the data was first collected, to investigate links between lifetime alcohol consumption and the development of colorectal cancers. In more than 20 years of follow-up, there were 1,679 colorectal cancer cases, with heavy drinkers, that's more than 14 drinks per week, 25% more likely to get colorectal cancer and 95% more likely to get rectal cancer, compared to people who drank less than 1 drink per week. They also found that heavy drinking throughout adulthood was linked to a 91% higher risk of colorectal cancer compared to constant light drinking. In contrast, they found no evidence of increased colorectal cancer risk among former drinkers who had a lower chance of developing non-cancerous tumours, which could then go on to become cancerous, than current drinkers averaging less than 1 drink per week, suggesting that quitting alcohol may well lower your risks. Scientists in the Pacific have sliced open nearly 900 dead fish caught by local fishers around the islands of Fiji, Tonga, Tuvalu and Vanuatu, finding that a third of all the fish they examined contained microplastic particles in their bowels. The findings, reported in the journal PLOS One, show severity varied between nations, with 75% of Fijian fish contaminated with microplastics compared to just 5% of fish caught in Vanuatu. While the amount of microplastics within each individual fish was generally lower than that in industrialized nations, the authors are concerned because Pacific communities rely far more heavily on seafood as their primary protein source. A new study has shown that ancient people transported a wild relative of the common potato across the southwestern United States, likely expanding the range of the species. The findings, reported in the journal PLOS One, show that granules of the humble spud was found on tills from 9 sites going back almost 11,000 years in areas between Colorado, Utah, Arizona and New Mexico. The authors say previous studies had already found genetic evidence that this particular species of potato was established from a population which was native to much further south. A new study has shown that people hunting for the legendary Sasquatch or Bigfoot are now using far more sophisticated techniques in their ongoing attempts to find evidence for the hominid's existence. The 3-year study of Bigfoot hunters by scientists at Cardiff University has concluded that those who are searching for squatches are drawing on increasingly sophisticated scientific methods to try and prove its existence. The authors found Bigfooters using a suite of modern technologies such as drones, thermal imaging systems, and parabolic dishes in their investigations. But as the skeptic's Tim Mendham points out, they still haven't found a single shred of scientifically verifiable evidence.
There's an article that came out recently that was pointing out that Bigfoot investigators actually like to use sophisticated techniques for collecting and validating evidence. In other words, they're trying to approach things in a scientific way rather than just in a conspiratorial way or a fantasy way. And that's fair enough. That's good. The fact that the technologies they're using are not particularly cutting-edge drones and things like that. But, I mean, it's common, and this is not a particularly new idea, but it's fairly common that Bigfoot hunters are actually quite hopeful of finding scientific proof rather than being anti-science. And the same would be, or it has been, similar amongst UFO proponents, although it's changing. And what you're finding is that, therefore, the Bigfoot want to see verifiable evidence. The trouble is what they're finding so far is not very good evidence, and the old story is that a lot of bad evidence doesn't add up to a piece of good evidence, it's just a lot of bad evidence. And in fact, the more bad evidence you have, the less likely something is to be real. Anyway, these people are looking at Bigfoot from a scientific perspective. There's obviously some problems with it, that Bigfoot suddenly is everywhere in the US, not just in the Northwest, Washington, sort of Oregon areas. It is all over the place in desert areas as well. So you start wondering if this animal is so prolific, there should be more evidence found than has been put forward. There's also people now verging, because of that, there are people verging into very unscientific areas, including sort of parallel universes and supernatural explanations for why they can't catch Bigfoot or whatever, even to taking photographs. That, they're always fuzzy photographs, and is this because they come from a parallel universe or have supernatural powers? Someone suggested actually that Bigfoot are just fuzzy animals, and that's the way they look. But it's an interesting phenomenon. The UFO people have gone further down the supernatural, unscientific areas because they're having trouble. They probably had a lot more sightings, in quotes, of UFOs than the Bigfoot people have, and it's a lot wider spread belief. But because there's so much bad evidence around, they have to find an alternative, an explanation for the bad evidence.
In the original Fighting Bigfoot series, they were looking for scientific evidence. They never actually found any, but they were looking for it.
That's right.
But then in the follow-up, the Expedition Bigfoot series, this is where they started speculating whether or not Bigfoot could be an alien or a supernatural being able to disappear and reappear wearing some sort of cloaking device or that sort of thing. It all became very Harry Potter, if you ask me.
Yes, yeah. Trying to explain away the bad evidence. It's a sad thing. It's admirable that they are trying to use scientific methods and trying to take a scientific approach to evidence. The trouble is, when the evidence is not there, or when it's very poor evidence, they are tending to move towards a supernatural explanation or a pseudo-scientific explanation. And the UFO people are well advanced down that area, and the Bigfooters are following in, whether it's an alien, whether it's a parallel universe or whatever. So they need to keep searching, and the trouble is, the more they keep searching, like UFOs, and they don't come up with the goods, and they're very wide searches these days, you start to wonder, is the phenomenon not real, rather than the explanation being wanting.
That's the skeptic's Tim Mendham, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.